So I'm Brandon Bloom. We're going to talk about dendrology, which dendrology is the study of trees. I actually didn't know this word, and then once upon a time in the Clojure IRC channel, oh, sorry, hit the button too many times. Gary Fredericks said this to me. He said, "B. Bloom is a dendrologist," because I was talking about processing trees, and I just loved this. I laughed really hard when Gary said this. Because as functional programmers, we work with trees a lot, and so we all really should be dendrologists, and we should be obsessed with trees and studying them and understanding them. So for, and here, he told us the Clojure bot, who said, I think it's German for, all right, so Clojure bot now knows that I'm a dendrologist, which just makes me giggle occasionally. So for this talk, I'm going to assume that you guys, being Clojure folks, you like data, you like immutability, you like values, you like all of these things. And so what I'm arguing is that this means you really like trees. So trees give you all of those things in many ways and makes them possible. And so I want you to kind of have like a new appreciation for trees and a few more tools to think about them. So the problem is that even though we generally prefer to work with trees, the real world is not tree-shaped, usually. It's this big spaghetti mess. And this little piece of parsley in the middle here is your beautiful functional program. Right? And I could not have found better clip art. This is the best clip art ever. I found this, and I giggled harder than when Gary told me I was a dendrologist. So I'm going to help you untangle the spaghetti in your brain. And so I realized I had a lot of stuff to say about this, like techniques and tools and tricks. But what I realized is that I just want to give you some two mental tools to help you untangle trees. They aren't going to be as detail-oriented of like, do this and that to process a tree. These are sort of like more higher-level thoughts that I'm going to go through that hopefully will enable you to have a new appreciation for what is a tree, how you design a tree, how you work with them at a conceptual level. So first, what's a tree anyway? Well, here's a tree. This is a tree. I've labeled it in breadth first order, A, B, C, D, E, F, G. It's got, it's variadic. You can have different number of nodes, whatever, right? You'll notice that all the pointers go from parents to their children. This is also a tree with all the pointers going from children to their parents. This is a different type of tree. Not going to talk about this type of tree today. This is what you see when you work with a database or the relational model or whatever. But the building blocks we're going to talk about today are all the pointers going from parents to children. So this is sort of the functional data structure trees that we're used to. So that's like the first thing. Those are different. Remember that.
So you're assuming a single parent?
The parent is implicit from context. So I'm thinking that the parents have their pointers down to their children. So in this diagram, each of these lines are pointers here. This is also a tree. This is a degenerate case of a tree. This is a linked list, right? But this too here is a tree. So some people don't think about it that way, but it is. So is this a tree? Well, this is a graph. It's a directed acyclic graph. And I'm going to make the argument that this is as good as a tree. So the reason this is as good as a tree is because there's a canonical serialization. You can just think of copying D from the perspective of traversing. And in that case, it's effectively the same as having a tree. And there's considerable advantages you can have by having the structural sharing that occurs with a directed acyclic graph. So this is an optimized tree. You can think of it that way, even though it's technically a graph. So the next question is this a tree? And this one is definitely not a tree. This is a cycle. This is for sure a graph, and this is not even an optimized tree. This is not a tree at all. And the problem with this is that you don't know where one tree starts and another tree ends if you want to think about this as a tree. Here's a real tree. This is called a banyan tree. Does anybody who knows what a banyan tree is? Okay. So a banyan tree grows a trunk, and then it grows down vines. And this is one giant banyan tree. And it grows all these vines down, and they reach the ground, and they turn into new roots, and they grow into new trunks. This is a mess. Where does one tree start and the next tree end? Whoever named this thing was like a crappy dendrologist, because this is a Banyan graph, is what this actually is. And so you don't want to like accidentally have your trees grow new roots and inadvertently create graphs. And like you thought you had a tree and then you don't. So the argument I'm going to make about this is that pointer cycles are the root of all evil. And the reason they're the root of all evil is because they're also the tail of all evil. Because you can't tell where the one cycle begins. You don't have an obvious starting point. You don't have an obvious canonical serialization. Pointer cycles are just friggin' evil. And I want to kind of explain to you why and make sense of that for you. So here's the directed acyclic graph we saw from before. In this case, this orange thing here is like an atom or like a loop variable. This is the pointer to the root of the tree. This green thing up here, this notation I invented, just saying I want to replace D through the path of B and rewrite it to BE. So this is green highlighted part here, saying I've got this path from B to D, and I want to rewrite at this path. So if I like do a swap on my atom or whatever it is I do, and I rewrite this, and I got A prime, B prime, and my new E here, you'll notice I'm preserving structural sharing, and I got a happy case where I efficiently only had to copy the path, and everything is fine and dandy. But if I've got a cycle, and I have a pointer to some point, which is not necessarily the root, right? It's just a part of the cycle, and I want to change this path B to D, and I do this, I have to copy the entire cycle. And that's true of this small case, but that's also true of all cycles ever, right? Even like this trivial example, like you can come up with ones where it's not a big deal or whatever, but the fact of the matter is that when I have a cycle, if I want to change something in the cycle, I have to rewrite the entire cycle. So how many people know what this is, have seen a system that looks like this? How many people have written this before? More hands should be up. You have all done this. Every one of you have done this. This diagram keeps me up at night. This is this simple single parent pointer in the code, right? I've got the parent pointer in my code, just one. In the code, there's literally one pointer going the wrong direction. And at runtime, it turns into all these other up pointers. And you have this cluster of nodes. And if I want to change G to G prime, I have to copy the entire tree. Stop doing this. Stop making graphs like this. Stop putting this one dopey up pointer that ruins the beautiful nature of a directed acyclic graph, right? And turns it into a cyclic spaghetti mess Banyan tree thing. Just stop doing it. Right? This is the one vine that came down and started the new root. So, like I said, pointer cycles are evil. But I want to go further than that. I want to say that pointers are evil. Just straight up, all pointers. Conceptually, they're the wrong model, and they're a really serious problem semantically for your programs.
So I hear what you're saying from a pragmatic perspective. So how do you find the
Let's come back and talk about that in a bit. Yeah, we'll come back to that. It's an excellent question. You'll find out in a moment. So the reason pointers are evil is just conceptually they're problematic because they're identities. And so what happens here, let's say I have this graph. Okay? In this case, this orange thing here is like a cross-reference or some other sort of node. It could be a parent pointer or whatever. Pretend this is, for example, a research paper, and this is like a LaTeX document, and this is like a section reference. Like in section D, please see section B. Right? This is a cross-reference. If I wanted to change B to B prime, I have a problem because D is still pointing to the old B. And so if I were to like traverse down this graph and follow this pointer, I have an old version of B, and so now there's two versions of B in my research paper. Like that's a problem. So I don't want this to be a pointer. I want this to be like a dotted line, a pointer, a reference, whatever. I don't want this to be a fixed relationship with a pointer to here. Because if I do another transformation, right, so I want b prime here to be what I point to in the context of this orange arrow. So when I make the change from b to b prime, I also have to move my root pointer to that new tree, and now I can interpret this cross-reference by the name b instead of by the pointer to that object. And so if I do another transformation, I don't have a problem now. Somebody else concurrently, in another thread, another function, whatever, can do another transformation and doesn't have to worry about this problem happening. Like, I don't have to worry about this being rewritten because I'm interpreting this in the context of that. So I can use the name b like a pointer as long as I have a context to interpret it in.
You're adding a level of indirection.
You have to add a level of indirection, precisely. And that's exactly what you do with a mutable pointer for your atom or something at the top, right? So I stole this slide from Rich Hickey, shamelessly. And I put his face down here so you know. So this dotted box here is an identity, right? And you do perception of it and its values over time. And so we all know that in Clojure we have atoms and agents and refs and other types of identities. But we actually have two identities in this diagram. There's this first one on top, right? That is, this is the identity of the current version of the tree. And then there's this one here, the pointer to b, the pointer, the cross-reference to b. So we have two identities here. And they're not necessarily atoms or refs or agents. So now to your question about pointers and references and things, let's talk about them. And I'm sorry, the first bit of code I'm going to show on the screen is C++. It's actually not really C++ because there's this like swear word thing here. I didn't know what to put there. I don't think it's totally invalid, but I figured this illustrates the point better than Clojure would. Here's a pointer class, right? Imagine for a moment C++ didn't have pointers for some reason. I have my global memory, right, at the top. I've got a pointer to some class t. I construct that pointer with an integer or a long. I have this deref function, right? This is the @ sign in Clojure. This is how you deref a reference or an identity. I do some voodoo to get out of t, that is combining the memory and this pointer. I can do pointer arithmetic, right? Because I know the concrete representation of a pointer, so I can like add something to it and get another pointer to another object. And all I got to do is hold on to that pointer value, and I can interpret that in the global memory at some point in time. But if we ignore the fact that it's a pointer and talk about it as a reference instead, we get rid of the arithmetic because we no longer have the knowledge of the concrete representation. We're no longer leaking that fact. We can do more things with this pointer now. As a reference, we can pin memory and garbage collect and do other things that you couldn't do if somebody was doing arithmetic on the pointers. And so this is a different abstraction than a pointer. And it's effectively the same thing. I just got rid of that operation. But the question now is, we still have this global memory. And so what happens if we thought about this without the global memory? Well, we still need memory here from somewhere. So one way we can get it is we can construct the reference with memory, right? We can store it as a second member of this object. And now I have a pointer, and if I dereference this pointer, I always get the same value in memory. And if I want that pointer to represent a succession of values over time, then I need to mutate memory, right? And so this deref here doesn't change the pointer, but memory may change over time. And so this thing I can pass around, and it points to a particular place in the memory it was initialized with, which may or may not change. But we're functional programmers, and so we like to have immutable things. So if we have immutable memory, this reference is useless to us. Because if memory doesn't change, then every time we dereference it, we get the same thing every time. It's not a succession of states. It's just one state. So we can move that argument to deref. So now this is two arguments, the current self, the reference, and memory, right? Like this, we only have the 1p private, whatever. In theory, we could have different things that implement this deref interface. But this deref takes an argument, which is memory. That's the context in which this reference is being interpreted. So if you want to think about this in closure terms, you've got your Igref, right? This is what atoms and thunks and other things implement. Delays, refs, agents, etc. You could imagine a protocol Igref in. It's just like Duref, but it takes an extra argument of context, right? And so this is how much more concise the closure is in the C++. I can do my voodoo magic here, but basically I take a private P, and I implement this protocol, Duref in, some context memory, right? So memory here is context for this instance of this abstraction. So let's do a concrete example of this.
So this was to make the analogy with the
Yeah, precisely.
You wouldn't normally make memory enclosure.
No, you wouldn't. Yeah, I mean, you could if you wanted to, right? So there's no reason you can't make a byte array if you have some knowledge about some case that like would benefit you to do that. Generally not. No. This is just to make that analogy. So here's a more realistic example of this. dbref. dbref takes a table and an ID, and then it's evaluated in the context where the context is the database, right? So I can make an object that I pass around that if I call dref in, I have to give it the database, and this gives me the current, for example, user 5, we Brandon. Give me the current Brandon in this database, or that database, or this database. But generally, you wouldn't do this either. This is just, again, to make that analogy. So what you would really do is you'd not bother with that abstraction at all, and you just write a get user function. But the point here is that in this case, 5, right, represents Brandon in the context of this database with get user, which has this part of the context, etc. This is an identity too, right? This is an identity. This is only meaningful in the context of like an HTTP request. This is an identity, right? This is meaningful in the context of like a database or whatever, but you need to know more stuff to be able to dereference this. You can't just assume global memory. This is an identity too. You know this is Brandon, this is me in the database, but you only know that in the context of the previous slides. So you have identities everywhere in your software, and you just got to remember the context, and so I'm going to give you a way to remember to think about the context all the time when you're talking about your entities. Context is king, and when someone asks you tomorrow, you're like, how was the talk? And you're like, it was good. Then he put the Burger King on the slides, and it really creeped me out. And somebody will be like, well, why was Burger King on the slides? What was the context of that? And you'll say, exactly. Context is king. So just remember to think about context. You're never going to forget that now because of that creepy face. Typed in king. Wanted to like cry, didn't sleep. It's terrifying. Does anybody else? Does this creep anybody else out? Anybody? Sorry. So let's talk about symbols, just to give you like a concrete example of what we were talking about. Give you the database example. Talk about symbols. They're sort of the original identity. Like before Rich ever talked about the epochal time model, right? Like Lisp programmers since the 60s use symbols as identities. So here's a piece of nonsensical closure code. You'd never write this, but it's just to illustrate the point. X doesn't do anything, right? It's this top level. X, it gets returned. This whole thing can be simplified down to like a function that returns local. But the point of the matter is that if I were to compile this, for example, to ClojureScript, which is a great example of how to like process trees, go look at the ClojureScript code. The way they handle context is like mind-altering how simple they made it. If you process this in context, this X, even though it's the same X as this one, they're different in context. And so you need to thread context through your analyzer, your compiler, your code generator to be able to do these things. This X is a var, this X is a local. At runtime, they're both the symbol X, right? But they mean different things in context. And so you can produce your contextually symbol resolved here, right? And so at this point in time, when compilation is occurring, right, that's that X, not this X. But context is not just about identities. There's other context that takes place in this compiler situation for this particular example. This one's a statement, and this one's an in tail position. And so therefore, because this is in tail position, we need a return, right? So it's really, really, really important that you think about context when you think about trees and working at trees, identities and context. So give you a couple more examples just to think about like what else is in context. Yeah?
And this actually goes beyond trees, though. This is just kind of just
It does. So when I started, so I came up with a title for this talk, and I had so much stuff to say about trees.
trees is great context.
There's just so much stuff. And so I decided that I just wanted to get across context and identities today. And so like there's about like a million follow-up questions, and I could literally ramble about trees for a month. But I just like want to get you thinking about them sort of the way I think about them, because I think it's a useful way to think about them. And so let's look at some examples of context in action. We've talked a little bit about identities in context, symbols, et cetera, databases, whatever. We're talking a little bit about just like some of the mechanics of context that you may or may not be thinking about, like there's context that you should be thinking about that you're overlooking. So I'm going to kind of like try and spell it out. Here's a vector encoding of this tree. Basically, it's a variadic vector where the first element is the label, and then the rest of the elements are the children. This is nice and concise. You can see it reads in breadth first order. You can encode your trees this way. You can work with trees this way. This is basically the same as your Lisp code is, right? It's a big tree of list. Do not do this. Do this instead. Make your stuff out of extensible maps. Like everybody starts with like Lisp and they like build tons of con cells and whatever, and then like you see people that do ML and Haskell papers and they have a new abstract data type, and then they're like, well, half the problem is that they have like a tree with decorated with numbers and they want to decorate it with different numbers, and they're like, all right, we got a data type for that, we're good. It's just like ridiculous because you're eventually going to want to decorate it with 2 numbers, and so like just always start with this representation. Just use extensible maps. Clojure loves maps. Maps are good for you. Extensible is good for you in terms of your data. Just like always start with this representation. You can layer this representation on top if you need that syntax. Just don't start there because you're just gonna like struggle, and then like all I'm gonna do is just associate another key and my life's gonna be easier. So that's like a practical thing in Clojure. So let's write some simple functions that do just that. They like annotate the tree with some context. So here I want to label all the nodes with their depth. A is at depth 0, B, C, and D are at 1, E, F, and G are at 2. So the function takes a node, and then it's just a very simple recursive algorithm. This is super easy. We have the recursive component F. We started off with a node and the initial value 0. We create a little function for annotating our children. We attach the depth onto our node. Like I said, extensible maps makes your life easy, right? Then we just like recurse into all the children and throw their depth on them with the incremented depth. Here, depth is your context, right? Depth could be a map, right? So Clojure does this. The Clojure compiler that I mentioned earlier does this, where they thread through a lot of context data in an extensible map. Here, it's just an integer. It might be a map with like 4 or 5 keys, whatever. I could stitch it onto the node itself in a context key. Like whatever it is, the point is you got to realize that like you have to thread some context through this traversal. And we have it on the way down. So we're able to like assoc onto the node on the way down through this traversal. All right, I said that. Here's a different function. I'm just going to make a couple. These are pretty simple examples. I just want to make a point with all this stuff in a bit. Basically, here I want to annotate the max depth. So these branches are max depth 2. And this branch in the middle here is max depth 1. And let's assume we already have our tree decorated with depths. So we have the same sort of simple recursive function where we get the max. If we're in an interior node, we get the max of all the depths of our children. Otherwise, if we're at a leaf, we just stick max depth on there, which is the current depth. And so this is an example of passing context back up the traversal. We have the depth at the bottom, but we don't have it till the way out of the traversal. We don't have it on the way into the traversal. So instead of it being an argument, it's a return value. It's part of node itself as an extensible key. It's part of the return value. So let's look at something a little bit trickier. So this is way trickier than you think it is. I started looking for a simple example to explain some of this stuff, and like I was blown away that there's like actual like research on like such simple problems. So if I wanted to number this tree depth first, right? I gotta like follow along that pattern, right? That's the depth first traversal shape, right? It actually involves passing the current index down and the number of children up, essentially, right? Yeah, you had a funny look on your face. You got it? Depth, yeah. So it's going to print out, if I were to print these, they'd print like this, right? So it turns out to be pretty tricky, actually, to number a functional tree like this, because what you need to do is you need to keep all the nodes above you to like stick stuff back into them when you're done. It's actually much easier just to print it out. So we'll do that first, and then we'll like think about the traversal, and then we'll think about the traversal plus putting it back together at the end. Here's printing these nodes, depth first recursive. Same idea, recursive function, initial value of 0. We're returning nil. We're not returning the tree. We're just printing it out. We're going to print the label and the index, and then we're going to loop for all the children, and then recurse. Like I said, we're not returning the tree here yet. So if I want to actually label the tree, I'm sorry, did we have enough time to read this? There's like, people know how to do a depth first recursive traversal? Pretty easy. Yeah, all right. Prefix, yes. So here now we want to label the tree. So this is trickier because we need to keep those nodes above us, like on hand. So here's our initial step with 0. We're passing in the index. Then we're doing, like we don't have the value yet to like label the next node, the sibling. So like we know on the way down the current index, but we don't know like the max index yet. So we have to like go to our children, and we need to thread through all the children this I value, and then we need to like pull that out as an argument, which goes to max index that we stick on the thing. So like we got to pass index down through the tree, and we got to pass max index up through the tree, right? And so this is starting to get kind of hairy and ugly, and like you can. So the problem here is that you're threading a value through here, where you need to like pass a value down and up. So if I were using, instead of reduce, right? So this is doing. That's exactly what's happening. So the recursion's unwinding here, right? This is recursing inside here, right? So you can write this simpler, and we will. But you see all this stuff, and this is like you have to like have that context of the tree in order to like relabel it on the way back out. And if you like have written any of this stuff imperatively, you're like, actually, I remember this being way simpler, like with state. And like it really is. If I just use a little bit of state, right? That's what that whole function turns into. It's like,
I don't agree with that.
Okay.
I think it's simpler recursively, but basically let the recursion handle the state for you. So that as the recursion unwinds, whatever state you normally would have needed to maintain
yes,
is being passed back to
you can.
You're still maintaining state on the stack.
Yeah, it's on the stack.
You're not maintaining it.
So I'm glad you said that, because that's kind of the point I'm trying to drive to here, is that there's context in the work you're doing, and it's hidden from you. It's on the stack.
Yeah.
And so if you're trying to figure out, like you want to work with trees, you need to think about that. You need to remember that, like, oh, I actually have a stack already, right?
Exactly.
So people forget that because they write a recursive function, and they don't realize that, like, at this point in the tree, there's some context. And so what we want, though, is we want something that looks like this, that's like this simpler, right? And like I've thrown the stack out. Well, sorry, I haven't thrown the stack out. I've encoded. Oh, this is iterative. Sorry, I forget what step I'm on now. So I've just like put this value through, and I swap it every time through. And this is like really simple, but I'm still doing the recursive traversal. And so in this case, the nodes are building up n on a stack. And there's this stack of recursive calls that have that state. And this is threading that index that through.
Are you trying to make this?
No, I'm just trying to make you aware of it, right? So.
I mean, are you saying that it's a bad thing to?
No, I'm not.
Maintain your state?
No, I'm not. I'm just trying to say that like, when you think about data structures and algorithms that operate on trees, or just in general, like you have to think that you have data structures you're working with, and you need to be like aware that they exist. And the argument I want to make is that it's valuable to reify that state. And so we'll talk about that in a moment. So where was I? Yes. So since we're smarty pants closure programmers, we know that state's an illusion, and we can avoid it. So let's do that again, following the same pattern of like, let's think about the printing case, and then we'll think about the numbering case, where we have to, like one case where we're just traversing it, another case where we're rewriting it. So here is a iterative depth-first traversal, which is much simpler than the recursive one. We'll work on an arbitrarily sized tree because we're not using the arbitrary stack that like can get blown off, whatever. Like we're allocating our traversal sequence on the heap. And this is pretty simple. We just start at index 0. We have the list of nodes to visit. If there's still nodes to visit, we continue. We pop the first node off. We put an index on it. And then we increment the index and go on to the children. The one thing I want to point out here is because we're now thinking about the nodes to visit as a data structure explicitly, we can do breadth-first traversal. All we got to do is take this and swap the order of them. Right? So instead of a stack here, we have a queue. So if we swap the stack out and put a queue in, we get breadth first instead of depth first. So if we weren't carefully thinking about the fact that we were leveraging the execution, the evaluation stack, we would have never made that realization, right? And so this problem happens at huge scale in programs where you've got a ton of data that's like hiding over here, over there, in the execution stack, and this database, and that thing. And you have to think about all the pieces of context that are relevant to the operations that are being performed. So we're getting closer to now we know we want to reify state, right? We want to have it and have our hands on it. So let's imagine for a moment we're looking at node E. And with the iterative traversal, we've got like this like stack of nodes we want to look at next, right? Those are like the stuff to our right. And then we also have to add more stuff to our context. This is the context of nodes yet to be visited. But in order to number the tree, we need to have the nodes we have visited because we need to rewrite them. So we also need like to have a stack of the stuff above us. And so with a pair of stacks reified, we can build our tree. So it turns out, I'm not going to go, in the interest of time, I'm not going to go into how you do this, how you think about this, how you do this. But we already have a data structure that is a pair, sort of stacks. Let's call it zipper. Clojure has zippers. There's some problems with the API. Sometimes you need different types of zippers they don't necessarily have. But the idea of a zipper is it basically reifies the traversal you have done and the traversal yet to do. And so it's very simple to make one of these. You give it a branching function. All of our nodes may have children. How to get the children, I just get the children key. How to make a new node, given it the old node and the new children, I just associate it and turn it into a vector, and then the root of the tree. And so if I have this zipper, if I have the right stack and the top stack and some other bookkeeping stuff that's all hidden in there, I can write this function, which is the iterative depth-first zipper numbering function. This is so nice. This is iterative. It works on trees of any size. At any point in this loop, I can print out the zipper and see where I am in the tree, what the state of the algorithm is. I've taken all of the context of this traversal and stuck it into these two variables. I no longer have to like do stepping and printing and debugging. I can literally just like print out the full state of the algorithm at any point because I very carefully thought about the context. So the way this works is that all of the traversal logic and all that stack management is bundled up into this znext function. It handles like walking down a depth-first search. And all I got to do is loop around until I get to a sentinel value for the end, and then just zip back up the tree and unwind the stack, right? So this zroot, this is saying I'm at the very end of my tree, and now I'm done. So this function internally just runs the stack backwards, just like you would when you return a value. So like I said, complete context in there. Yeah.
So I think this is really cool. The Haskell people might be freaking out because they introduced state functions. And I just want to know what your view is on that.
This state, you mean?
Yeah.
I mean, okay, so no, that's fine. So when you program, you have to write things that evaluate and do work. And so the Haskell people are like, oh, hey, we have laziness. We're not strict. Great, that's wonderful. But like, you still have a policy for how evaluation works. It's demand-based evaluation. If you have strict evaluation, then you say, look, I know that I have this illusion that what I want is the return value and that this is a function to generate it. But it's not really a function, it's a procedure. Let's be honest. Strict programs are procedures, right? Lazy programs are procedures as well. They're just slightly more flexible in some ways. And we can talk about laziness. I have some bonus slides if you want, where I think that laziness is a major problem because laziness introduces graphs, right? So I can actually create cyclic data structures, at arbitrary levels in a Haskell program and like lose the ability to do structural sharing and things like that. And so like laziness has costs as well. And so I could, in theory, come up with a language that's like, well, this function's strict and this function's not strict and this function does that or this one does that. But the bottom line is that our language we have here, it's strict and this is a procedure and I've turned it into an iterative operation by reifying the stack, which I know exists. I'm not pretending it doesn't, right? And so like I'm being realistic, which is a marked trait of Clojure programmers.
I actually agree with that.
Excellent. Then I'm glad you asked. So did I lose anybody like really majorly? Do people get why this is cool? Yeah.
Is the basic idea that the state is always on the stack? It exists in the physical world?
No. Okay. So the point is that the evaluator has some state, and the evaluator has some context for some piece of code being executed, right? My point is that when you think about trees or just general data processing in general, right? Like you need to think about the context of your evaluation, of how you interpret data, whatever. So one thing you really need to think about is identities. So you got to think about like number 5. Is this Brandon or is this an integer, right? The other thing you need to think about is like all the little bits and pieces of your code that you haven't given careful thought to that are like hidden in places. So one of like the benefits in functional programming when you have like everything's immutable or whatever, and you want to thread some extra data through, what do? You add an extra argument, right? And so you took something that was implicit before, some global, some whatever, and you made an extra argument. And so now you can see the complexity of the problem, like, and feel it, right? A lot of times it's like, I have a giant global that's like the current world or whatever. And when you do that, like, that's an argument to all of your functions, but it's not in the signature of the function. And so one of the problems people have when they learn functional programming is that like they're like, oh my god, I have so many arguments, and they're like, oh, this is so complicated. And that's not the case. It was already complicated, but it was implicit. They weren't thinking about just how complicated it was. And so when you take things that were implicit and make them explicit, right, that helps you reason about them and makes the complexity apparent. And so does that answer your question?
Or allows you to change it.
Or allows you to change it.
Now that you made it explicit, you can actually do something different.
Exactly. So that was the example with breadth first versus depth first. I took a stack, replaced it with a queue. It turns out that I can actually do breadth first numbering with zippers. I couldn't figure out how to get it to fit in the slide and mirror exactly right, and my head was hurting, and I wanted to practice the talk rather than hack it. So if you really want to melt your brain, you can read these 2 papers. There's actually the guy who invented all these functional data structures that Clojure uses, literally wrote a paper about how programmers have a hard time figuring out purely functional breadth first numbering because of this problem. Like, these are like computer science researchers. You like informally interviewed a bunch of like computer geeks, and they're like, holy shit, I can't do a breadth first numbering? It shouldn't be that hard.
The thing is that depth first uses the stack naturally.
Exactly.
Breadth first uses the
Precisely.
queue, and it's hard to write a queue recursively.
Precisely. So actually, the way that the secret is that you create a zipper over a forest. So instead of having a tree and you zip over that, you have a tree where going down in the tree is actually going to all the children of that level. And so then that creates a zipper. And then as you go, these 2 papers cover it. They explain it. Clojure's zipper API would not enable me to create the nice turn concat around. And so I think there's some serious problems with Clojure's zipper API. There are ways that I could like tweak the API such that all I have to do is swap out the zipper constructor, such that like if I get rid of this zipper constructor and put in that zipper constructor, then I get a breadth first instead of a depth first search. One of these days I'm going to write my own zipper library because I want to be able to do that just to say I can. So these talk about breadth first numbering in particular, and this talks about just in general like zippers and iterators and other purely functional data structures like this. And so I spelled it out a few times. But the key ideas of this talk, like the 2 things you need to like sink into your brain before you can get into like even more mechanics of like working with trees, is that you need to carefully consider identities and context, right? So we talked about identities and all that stuff. I've said it like 12 times. In context, I've like showed you that example and reifying. You want to like, when you're designing the schema for your trees, right? You got to say, here's my tree. This is what it looks like. Here are the identities. Here are the cross-references. Here's what this means at this time in this place, and this is how it's represented. And then when you're working on those trees, you need to think about, like, OK, here's all the stuff that's relevant at this point in time. Here's all the things that influence the behavior of the tree in this algorithm at this place. You need to think about identities in context. And if you do that, you'll have happy trees. You'll be a happy dendrologist. And you'll look like me. Like that. So hopefully that helps. Happy to talk about trees forever. So thanks.